So today I will talk about the Durham-Witt complex and how and the calculation of T88 and the TR groups for smooth algebras over a perfect field of characteristic P. So let me recall that by analogy with the motivic spectral sequence for K-theory, one should have a sequence like this. And that such a spectral sequence now exists by the work of Barth and Scholze. Maybe not for general X, but for X over a perfect for X defined over a perfect field or a perfectoid base, and I think more generally. But so how does this look? The E2 term looks like this, and then here on the fiber line, where in the motivic spectral sequence you have Milnor K-theory, we now have this Durham-Witt complex. And then if we're in characteristic P, then we have a polynomial algebra on this divided Bott element that we saw last time. This has slope 1. And so here we have alpha squared and so on. So the spectral sequence sits in this band. So in the same way as Milnor K-theory is, so what is this? In other words, here in degree J, this is HJX of this, and we should think of this as a calculation of this group. This has not existed until very recently, and whereas this is much older. So, but in the same way as Milnor K-theory is defined by generators and relations, and it's really a calculation of a particular motivic cohomology group, in the same way this is defined by generators and relations, and therefore it's quite difficult to work with for certain things. For example, if we have a finite flat map from X to Y, then there should be a push-forward map on these groups, and we don't know how to make that. At least I don't. I don't even know how to make that on Kähler differentials. Okay, so now let me give the definition of what this is. So this is the Durham-Witt complex is defined to be the universal example of an algebraic structure called a Witt complex, and so I will define that. So I will do it in the p-typical case. So let's see. So let P be a prime. A prime number, and let A be a commutative ring. So today all rings will be commutative. Then a Witt or a p-typical Witt complex over A is then a pro anti-commutative graded ring written like this. So en minus 1 I'm going to use the classical indexing so that we index by positive integers. Jim Borger prefers to index by non-negative integers, and I think that's a better way of doing it, but I will stick with this here. So we have this. So the maps in this pro system are called R, and then together with a strict map of pro rings from the bit vectors of length n in A to the ring in degree 0, such that the restriction map here is compatible with the structure map in this pro-abelian group. And strict maps of pro-abelian groups. Let's see here. So let's see. So a map D that leaves the level alone, but raises the degree by 1, and maps F and V. That leaves the degree alone, but respectively decreases and increases the level by 1, such that the following hold. One for all x here and y here. D of x times y is dx times y plus minus 1 to the degree of x times dy. So d is a graded derivation. But d is not in general a differential. So dx is d log lambda of this square root of 1 in the Witt ring times dx. So topologists know this square root, or this d log of this square root very well, because that's the Hopf element eta. So this is a different name for the Hopf element eta. Yeah, if p is not 2, then this is 0. So d is a differential if p is odd, and but if p is 2, it's not. And d log here means, so d log of a unit is u inverse du. Next, if composed with v is p times the identity, and if and V satisfy a projection formula, so for all x in E in I and y in E in minus 1 j, x times v y is v of f of x times y. And for all y here, if dv of y is dy, but then plus a term. So again, if p is odd, this term vanishes, but for p equal to 2, this survives, so we have d log times this. So we have this class, this thing which is eta times y here. And then finally, for all A in the ring A, not the Witt ring, if d lambda of the Teichmüller of A is the Teichmüller of, oops, I forgot the lambda. So this is the Teichmüller of A to the p minus 1 d the Teichmüller of A. Yeah. So So this is the definition. A map of p-typical Witt complexes over A is a map of pro-anti-commutative graded rings, which commute with all this structure that I have written down here. It's just a diagram indexed by this. Only if I want to say that something is a pro-isomorphism. Yeah. Well, maybe at some point, but actually not today. So. It is. Did I not say that? It does, yeah. So we should write that somewhere. Thank you. Yeah, and then by definition, the p-typical, the Rham-Witt complex over A is well, is an initial object in the category. Of p-typical Witt complexes over E. So this definition has a long history. So first, Bloch defined such a complex by using K-theory. So using the observation that Witt vectors is or p-typical Witt vectors are the p-typical curves on the multiplicative group. And at that time, Quillen had just defined this sequence of functors extending the multiplicative group, and then he defined such a complex built out of the p-typical curves on K-theory. Then Dulin and Ilussi noted that this can be constructed completely algebraically, and they did that for FP algebras. And then Yves Madsen and myself proved that such a thing exists for any ring when P is odd, and my student Viorel Costiano corrected the definition for P equal to 2, where it's important that you have this term, and constructed this when P is 2. I should say that when Dulin and Ilussi defined this, so for them the hard part was to get this divided Frobenius. So you can see here that if I should let me say here that the defining relations imply that df is not fd but is pfd. So f is like a divided Frobenius, and similarly vd is p dv, and let's see, I should yeah, and also so I already said that when P is odd, this class here is 0, and if P is 2, it becomes equal to this sum, 2 to the s minus 1 dv to the s lambda of 1. So this is P equal to 2. So this is what the class eta Hopf element eta looks like in the Rham-Witt complex. Yeah. So, but the construction of this initial object, well, you can see that an initial object exists by using the Friedel joint functor theorem, but that doesn't give you much control of what it is. But the construction has been greatly simplified by an observation of, I think, first Borger and Wieland, that, let me write that, that there exists a canonical natural transformation on the Kähler differentials of the ring of p-typical Witt vectors such that f of dA, where A is in the ring of Witt vectors, is equal to p d of fa. So this divided Frobenius already exists on the level of differentials, and now you construct the de Rham-Witt complex as a quotient of the de Rham complex, then the Frobenius, this divided Frobenius on the de Rham-Witt complex is just the one induced by the divided Frobenius on the de Rham complex. So this construction here uses the theory of lambda rings, and this is what you get by asking yourself the question of what modules over lambda rings are and derivations over lambda rings are. Let me, to give an idea of what what this looks like, let me say what you get for the ring of integers. So if A is C, then Wn omega A naught is the ring of Witt vectors, and this you can write as follows. It's the product. So as an abelian group, it's the product like this here. And now the product in this ring is given by the defining relation. So let's see. V, so if S is less than or equal to T is here, then V is, let me not write the lambda, times Vt of 1 is, now we can put this S inside using the projection formula. So this is Vt let's see. Yeah, sorry. It's Vt of f t Vs of 1 times 1. And now if V is P, so this gives P to the S Vt of f t minus s of 1 times 1. But f is a ring homomorphism, so this again is just 1. So this is p to the s Vt of 1. So you can, so now you can see how we multiply the additive generators in this abelian group. Can I erase that again? No. It's not yeah, so obviously it has 0 divisors. Yeah. Well, maybe I can write it here. So now in degree 1, this is the product of the differentials of these generators here. Whoops, that was not right. like this. So because VD is, or PdV is VD, so if I multiply this by P to the S, the D comes all the way inside. And since D is a derivation, it kills 1. So P to the S times this class is 0. And the claim is that nothing before it is 0. So this is the largest that this group could possibly be. And the claim is that there are no further relations. And then in degree 2 and higher, we have 0. Like this. Yeah. So the restriction map is given by. So now I will just see. I will only.
In this description, is there any way to see the special role of Rham?
That's we're coming to that. Yeah. Yeah. So that's what we. So here with the restriction map does not see that. So the restriction map commutes with everything, and so it goes all the way in here and just makes this n1 smaller. So this is the product. Oops. So it just kills the last component and leaves everything else unchanged. Like that. So, but now the Frobenius is different for p equal to 2 and p odd. So f of, how did I write it? 1. Here, so let's see. So let me write here. So while for p odd, so for p odd, if dv is d, so so when we have 1 here, then if dv becomes d and d of 1 again is 0, so it annihilates the first, the component is equal to 1, so we get here the sum A is bar dv is minus 1 lambda 1 in minus s, and then now we reindex that as sum here a t plus 1 bar dv t lambda in minus 1 minus t. The bar here is because now AS lives in C mod P to the S C, and it's now mapped into C mod P to the S minus 1C, so it loses. So this is the residue class. And for P equal to 2, we instead have that this is the sum 2 less than. So now the first, so A1 survives, and get that this is 2 to the s minus 2 a1 plus as bar dv to the s minus 1 lambda. And when we reindex, then this is 2 to the t minus 1 a1 plus a t plus 1 bar dvt. Like that. Okay, so what is the consequence of that? This is that, let me write it over here. So the formula for these groups is the same for all p.
So A1 leaves in a group of, that is in an F2 vector space, right? So the only contribution in T is 1. Is this right?
No, because remember that this lives in dvt lives here. So it contributes to all of them.
All right, it's just because usually you were very careful with denoting residue classes somewhere, but A1 lives in an F2 vector space.
So therefore 2 to the t minus 1 times it lives here. Yeah.
You unbar it. Never mind, okay.
Yeah. So what this means is that for all p, we get the 1 units in the p-adic units sitting as the image by d log Teichmüller in the inverse limit here, and it's so this is isomorphic to the fixed set of the Frobenius on that limit. So remember here when p is 2, so when p is phi is f, but there's also the change in, so that's why I call it phi now. So when p is odd, there's no torsion in here. So this is isomorphic to the p-adic integers via the logarithm. And but when p is 2, there's a c mod, there's plus and minus 1 in here, and d log minus 1 now becomes the class. So let's see, so here, so in particular, f of d log minus 1 is f of sum 2 to the s minus 1 dv is lambda 1. But now you see that this is precisely preserved. Because A1 is 1 and all the other A's die because they are as high as they can be in the two-adic filtration, and then this 1 gets spread out and gives back all the things we had before. So yeah. this group here is isomorphic to T R C P, or let me write it like this. This is isomorphic to TC 1 of C. Yeah. Nah. So let me come back to this spectral sequence picture that I had in the beginning. So here for C, the de Rham-Witt complex just has two components, and then in the rest of the spectral sequence, everything should sit on this line here. So there should not be anything on this line. And yeah, so this group here is H1 of X with coefficients in W of P minus 1. And when P is 2, this just happens to live on this line. When P is larger, then this is going to live out here somewhere. Oh, it's going to live somewhere here. So if P is odd. And so we should see, in general, we should see alpha in pi to P minus 3 of the sphere in this group. So this difference between P odd and P equal to 2 that we see here in degree 1, we should see in this complex here in general, but up in twist P minus 1. And yeah, so it would be nice to understand that.
Does the rest of the two primary semi-noncommutative groups of spheres have any shadow? Is that any of this visible?
I don't think so. Oh no, eta squared is 0. Yeah. Which I just told you. Because W omega 2 of the integers is 0.
Are any of the longer polar brackets non-zero? Eta.
I don't know. Yeah. Yeah. Let me write a theorem here. So for every, well, Yeah. So the groups T, R, N, I. So if we write this in terms of equivariant homotopy theory, we can write this as S I like this, and Tom Dieck calculated long time ago what the maps between these spectra, these equivariant spectra, look like, and they precisely give you these maps FV and the relations among them. And then the map R uses also the cyclotomic structure of T88. So these groups have the structure of a p-typical Witt complex over A, and therefore there's a unique map from the initial such structure. And this map is an isomorphism for I equal to 0 and 1. There's nothing here below 0, and if A is the integers, then it's also an isomorphism for I equal to 2. Yeah. Okay, so let's have the break now, and then we will talk about polynomial extensions after the break.